Can a computer discover the cure to cancer? Will a robot be able to drive a car? In both cases, we'd have to use artificial intelligence to solve those problems. What does it mean for a computer to be intelligent? To answer these questions, let's look at a thought experiment. If I show you this picture of a cute puppy, how do you know that it's a dog? And what about this picture? What do you see? Of course it's a giraffe. Now try to explain why you saw a dog in the first picture and a giraffe in the second. It's hard, right? And what if I only show you what the computer sees, the pixel values of the image? Does that look like a dog? The same way that you found it hard to explain why you saw what you saw, it's incredibly difficult to simply tell a computer when it is looking at a dog from a grid of pixel values. For this reason, a computer has to learn for itself what it means to see a dog. Today, neural networks, a subset of machine learning, which is itself a subset of AI, have been incredibly successful at developing intelligent algorithms. Neural networks emulate the human brain by connecting neural-like units to find patterns in large sets of data, and make predictions about new, unknown pieces of data. The secret to learning, and thus intelligence, lies in determining the strengths of these connections. So how does a computer refine these connections, or weights, to make accurate predictions? The first step is to find a way of measuring how far off our prediction is from the real answer. This is typically called the loss function. To visualize this, let's take the example of rolling a ball down 2 ramps with the goal of making the ball in a bucket. The only thing we can change is the angle of the ramps. For most configurations of the angles, the ball will not land in the bucket. So how do we fix this? First, we can drop the ball down the ramp and measure the loss, how far the ball lands from the bucket. If it lands in front of the bucket, we've undershot, and we need to increase the slope of the ramps, and vice versa. Each time, we make small changes to the ramps so we do not overcompensate for our error. Eventually, after many practice runs, we will have found a good configuration for the ramps that almost always gets the ball in the bucket. Going back to the example of dogs and giraffes, we can take a similar approach to teach the computer. For instance, if we show the computer a picture of a dog, ideally, it should be 100% confident that it sees a dog. If the neural network outputs that it is only 60% confident, we've undershot. The same way we made the ramp steeper when we undershot the ball. Now we can increase the strength of the weights to make the confidence higher. We keep showing the network different images of dogs and giraffes and making small changes each time based on how far off we are from the truth. If we take the simple example of a network with 3 neurons and 2 weights, we can imagine what is going on a 3-dimensional graph with the weights on the x and z axes and the loss on the y axis. Each training example tries to push the model towards the lowest spots on the graph, wherever the error is the smallest. In order to find out where to move, we use some calculus to determine the slopes of the graph around our current position and follow whichever direction points downhill. With larger models, it's really the same idea, except since there are more weights, the dimensions of our graph are way beyond anything we can picture in our heads. The implications of AI are massive, from self-driving cars to more accurate medical diagnoses. The sky's the limit with AI. So get out there, start teaching a machine to think just like you, and change the world.